Alright, number 28. So, we got a flywheel of a steam engine moving around in a cycle, and then it comes to a stop in a certain amount of time. The original velocity, angular velocity, make sure I'm in pen mode here, is 150 revs per second. Sorry, minute. Ooh, it's big. Revs per minute. The time required to come to a stop is 2.2 hours, and since we're in minutes, we're going to convert that to hours. That's just times 60, 132 minutes. And we come to a stop. Omega final is 0 revs per minute. So part A is asking what is the angular acceleration? So we can use kinematics for this. So omega final equals omega initial plus alpha t, and 0 equals 150 plus alpha times 132 minutes. So alpha equals negative 1.14 revs per minute squared. And they wanted us to leave that in revolutions per minute. I know most of these problems we convert revolutions to radians, and in fact in this problem we also have to convert to radians at some point, but this is a valid unit. Alright, that's part A. Part B wants us to find how many revolutions the wheel makes before stopping. More kinematics, so we can use theta equals omega initial t plus 1/2 alpha t squared, and we're looking for theta. Theta is, so we start off at 150 again, and we go for 132 minutes plus 1/2. We just found our angular acceleration, negative 1.14, and so we'll use that times the time squared. So theta is 9,900 revolutions. Piece cake. Part C wants us to find at the instant the flywheel is turning, so at the instant the flywheel is going 75 revs per minute, meaning it's slowed down from 150 to 75. That's 140. So that's yeah. Anyway, so at that moment, what is the tangential component of the linear acceleration? So that we can get from the expression where linear acceleration is angular acceleration times the radius. This is one form that you could get for tangential acceleration. You could also use linear kinematics, moving around a circle, because when you're moving around a circle, you could straighten the circle out, make the circle like, if you had a hula hoop, you could, or a string that was in a circle, you could cut the string at one point, and then, well, just do this, right? So you have a string in a circle, snip it here, and then you can straighten it out, right? So the length of this is 2 pi r, just like the circumference is 2 pi r. Anyway, you could use linear kinematics along a line to get the tangential acceleration, because your tangential acceleration is your acceleration at any point tangent to the circle, and that is moving along the line, the direction of the line at that point. But this is another way of getting it, because your angular acceleration is constant everywhere, but in order for that to happen, the farther out you get, the more you have to accelerate to make up for that, because you're covering more distance, right? If you're only here, you cover this distance. If you're out here, you cover this whole distance, a much longer distance. Anyway, long story short, so let's do that. This is going to equal negative 1.14 revs per minute squared. And we want linear acceleration. That has to be in meters per second squared. At least that's what the book wants. It's a 4. So we're going to convert this to radians and then to seconds. So we know that there's 2 pi radians in 1 revolution. And we know that in 1 square minute there are 60 square seconds. And so that takes care of alpha, that converts it. And the radius right here is half a meter, 50 centimeters. So that turns out to be negative 9.9 e to the negative 4 meters per second squared. And that's our tangential acceleration. Now in part D, we want to find the magnitude of the linear acceleration. So that is made up. So if we're moving in a circle, right? Let's say we're here. We would have a tangential acceleration. Let's say we're going, in this case, since it's negative, we have to be slowing down. It has to be going opposite the direction of motion. So here we would be moving counterclockwise around the circle. So to slow down, the acceleration has to be clockwise at that point. So we have a tangential component and we have a radial component. And together, a tangential and a radial, which by the way you should recognize as centripetal acceleration, gives you a net. Right? So that's what we're doing. To get a radial, we know it's centripetal acceleration. A radial is v squared over r. We need v. So what's v? V, we can use a similar expression that we used here. V is omega r. And omega at this point, this is the point for part C, we're going at 75 revs per minute. And we have to convert that to 2 pi radians per rev times 1 minute per 60 seconds. I might be hitting the edge here. And then that's also going to be times the radius. Maybe I'll do that here. Times 0. times 0.5 for the radius. So v equals that. The radius is just here, yeah. So that turns out to be 3.93 meters per second. That's our v. That goes up in here. So we get AR is 3.93 squared over 0.5 is the radius. And that gives us 30.8 meters per second squared. So we got 30.8 as this component, the radial component. We got negative 9.9 e to the negative 4 for this one. This is tiny. So even when we Pythagorize, you can probably guess that it's not going to be much bigger, bigger than this number, especially if we round to even like 2 or 3 decimal points. But let's just do it anyway. So a net is the square root, this is the Pythagorean theorem, of AT squared plus AR squared, and we're going to plug in negative 9.9 e to the negative 4 in here, square it, makes it positive, and it makes it even smaller. AR is 30.8 squared, square root that, and basically get the same answer because of rounding. This would be slightly larger than AR. Not too shabby. Alright, sorry. Alright, next problem is problem 34, looks like. Later.